So now let's take a look at the behavior of a gas if its volume is fixed and you have a fixed amount of gas as well. All right. Starting off with the ideal gas equation, PV equals nRT. Let's rearrange our this equation so that we have our variables on one side and our constants on the other side. So N is a constant here, so I keep it on the right. Volume, I want to move that to the right, okay? And R is, of course, a constant. I'll keep it on the right. And I want to move my temperature over to the left. I want to put all my variables on the left side, okay, just so we can see what the relationship is. Okay, so if I did that, I say PV equals nRT. So I want to get rid of volume from the left side, so I divide both sides by the volume. That gets rid of volume from the left. And then I want my temperature. Since it's a variable, I want to put it on the left, so I divide both sides by temperature, so that gets rid of T from the right. So I get P over T right here is equal to NR over V, and that's the rearranged equation. And I'm rearranging it so that everything on the right is a constant. Number of moles is constant, R is constant, volume is constant. So P over T is a constant, and again here you see the ratio of two things is a constant, then that means those two things are directly proportional. So significance of this result is that you can say for a fixed amount of gas at constant volume, pressure and absolute temperature is constant. In other words, if you have a fixed sample, if you have a sample of gas, volume is fixed. If you're going to heat that gas, its pressure is going to go up. Okay? You double the temperature, the pressure will double. Okay? Temperature goes up, pressure goes up. You cool it down, the pressure will drop. And again, just like in Charles's law, you have to use the Kelvin temperature for this. Now, this relationship between pressure and temperature, this direct proportionality, okay, is known as Amontons Law. Now, you may find this in some textbooks as being referred to as Gay-Lussac's law. Okay, so there's probably more textbooks that actually call it Gay-Lussac's law than Amontons Law, but I've read the arguments about calling it Amontons Law. I kind of agree with the arguments to call it Amontons Law rather than Gay-Lussac's Law, based on historical accounts. Okay, but just be aware, just whatever textbook you might be using, depending on the textbook you're using, you might see this referred to as Gay-Lussac's Law. Anyway, what happened? What would a plot of pressure versus temperature look like? So if you were to vary the temperature, how would the pressure depend on it? If you are to hold the volume constant, so constant N and V, right? Well, let's look at our equation. P over T is equal to NR over V, right? So we can say that P is equal to NR over V times T, okay, plus 0. Adding 0 does nothing, right? But I'm writing it that way so you can see how the graph is going to look. I'm going to plot P on my y-axis, so this is my y. And I'm going to plot T on my x-axis, so this is my x. And NR over V is a constant, so that means y is equal to some constant. We're going to call that constant m. That would have to be the slope of your line, right? Plus 0. So this is gonna this equation is of the form y equals mx plus b. So if I were to plot pressure versus temperature, anytime you're plotting two quantities that are directly proportional, you're gonna get a straight line with an intercept of 0. Okay? What's our slope going to be equal to here? Is equal to m, which is equal to nr over v, right? Our slope is NR over V. Okay? That's the slope right here, NR over V. So this graph, every point on this graph was taken at the same volume, constant volume, same. And so this curve right here, all of the points here, okay, belong to, we say, to the same isochore. So constant volume, data collected at constant volume are said to be on an isochore. Okay, so isobar, constant pressure, isotherm, constant temperature, constant volume is isochore. So that means if I had some pressure here, P1 and T1, and I want to know what would be the pressure at T2, then I know that this P2 over T2 must be equal to P1 over T1. So any point on this graph will have the same value for P over T. All right, so let's take a look at an example. You have a fixed volume container of gas, contains, it's at 300 Kelvin and is at 1 atmosphere pressure. We double the temperature, what do you think will happen? From 300 to 600 Kelvin. You also double the pressure of the gas. Okay? So you would expect your answer here to be 2 atmospheres. And you can write the equation here. P1 over T1 equals P2 over T2. Okay? So how do we know just by reading this problem that we're dealing with constant N and V? Okay? You have a fixed volume container, so that's constant V. Okay? And it says it contains a gas. It doesn't say anything about losing the gas or adding more gas in, so you can just assume your N amount of gas is fixed. So N is also constant. So P1 over T1 equals P2 over T2. We're calculating the final pressure, so I solve for that by multiplying both sides by T2, right? That will cancel my T2 from one side. So P2 is equal to T2 times P1 over T1. Or I can rearrange that. I can say P1, which is 1 atmosphere, times T2, which is 600 Kelvin, over T1, which is 300 Kelvin. Okay? And so 1 times 600 over 300 is going to be 2.00. In effect, by doubling the temperature, you're doubling the pressure. Pressure and temperature are directly proportional, provided you are dealing with a fixed amount of gas and the volume is constant when that change occurred.